So in this video, we're going to start with Chapter 3, and we're going to start looking in Chapter 3 at exponential and logarithmic functions. In this module, we're going to focus on exponential functions. So there are two types of exponential functions, we could say. One is called exponential growth. And here we have a graph of exponential growth where we have some coefficient a0, and then this a here is what we call the base of the exponential function. And in this case, a is greater than 1, so that means that the graph is going to increase from left to right, and it's going to grow without bound. It's going to grow forever. To the right here, we have something called exponential decay, and in this case, our base a is between 0 and 1, and so in this case, we can see that our graph is decreasing or decaying and get closer and closer to y equals 0 as x gets closer to infinity. So there's a few things we could say about these graphs. In this case here, both of these cases, we have what's called a horizontal asymptote at y equals 0, and that's going to turn out to be important. And for both of these, the range of the function is going to be between 0 and infinity, and the domain, we can put any x value we want, is going to be from negative infinity to infinity. So an example of exponential growth might be something like f of x is equal to 2 to the x. So in this case, we have a number that's greater than 1, which is 2, that is our base, and this would be a function that grows from left to right. And for exponential decay, we might have something like f of x is equal to 1/2 raised to the x. And that would make our base a number between 0 and 1, and this is why the graph would decrease from left to right. So another way that I could write this f of x equals 1/2 to the x is I could also write f of x is equal to 2 to the minus x. And in this case, my base is between 0 and 1, but since I is greater than 1, but since I have this negative here, that would put this 2 in the denominator and make it 1/2. So this would also be a way that we could represent exponential decay. And again, in each of these cases, we have a horizontal asymptote at y equals 0. The range is from 0 to infinity, and the domain is from negative infinity to infinity. Okay, so it turns out that there is an important base that's going to come up quite a bit in this class, and that is the base of e. And e is what's called the natural number, and it's an example of something called an irrational number, which means that it is a number that's got decimals that repeat forever, that go on forever without ever repeating. So we might have something like this if we looked at the first few digits of e. And this base is going to turn out to be the most important one that we use for this class. So what we'll usually do is say something like y is equal to e to the x. This is going to be our exponential growth. And y equals e to the minus x. This is going to be our exponential decay. Okay. So e has kind of a special definition that we can write using limits, and e is technically the limit, or one way we can write e is the limit as h approaches 0 of 1 plus h to the 1 over h, right? And what this is saying is that as h approaches 0, this term in parentheses is getting closer to 1, but it's never getting exactly to 1, and we're raising it to an exponent 1 over h, which as h goes to 0 is getting to infinity. And so what ends up happening is these two things balance out, this number getting closer to 1 and the exponent getting to infinity, and that ends up giving us this number that we could get if we plug into our calculator. Okay? An alternative way of writing this would be e is equal to the limit as h approaches infinity of 1 plus 1 over h to the h. And that's basically just saying the same thing, except now instead of making h approach 0, we're making h approach infinity, and that makes this 1 over h get closer to 0. Our exponent gets closer to infinity, and so this here is going to also be this irrational number, 2.718, approximately going on forever. Okay, so what we're going to be interested in is looking at how to take the derivatives of y is equal to e to the x and y is equal to e to the minus x. And to do this, we're going to have a fairly simple procedure. All right, so the thing that you need to remember for now is that this is theorem 1 on page 299. And this says that if f of x equals e to the x, then df dx is also equal to e to the x. Okay, so this says that the derivative, and this is also we could write as f prime of x, the derivative, or the first derivative of e to the x is e to the x. And one way we can think about this is if we look at a graph of e to the x, which is going to be exponential growth, because e is a number that's bigger than 1, then what we'll find is that any particular value, so let's say this is our x, and this is e to the x, the slope of the tangent line, which we know is f prime of x, is going to be the same as the function value at that particular point. So the slope of the tangent line to e to the x at x is the value e to the x, the value of e to the x. Okay, and so that's a very unique property of the exponential function when we have a base e, is that the slope of the tangent line to the graph for any value x is the same value as what the function is at that value of x. Okay, so this turns out to be important, and this formula here is what we're going to use to solve a bunch of the problems that we're going to start working on. So let's say that we just look at a simple example, and that example is y is equal to 3 e to the x, and we want to find dy dx. So what I could do is take the derivative of both sides, so dy dx is equal to d dx of 3 e to the x, which if I use a constant multiplier rule is 3 times d dx of e to the x. And then what I can do is I can say that d dx of e to the x, based on the theorem from the previous page, is just e to the x, so this is 3e to the x. We could also combine something like this with the product rule. And so let's say we have y is equal to x squared e to the x. Then what I would do is I would say this first function, x squared, is my f. The second function, e to the x, is my g. And then I would say fg prime is equal to fg prime plus gf prime. And that's going to be f is x squared. And g prime is a derivative of e to the x, so that's going to just be e to the x. And then plus g is e to the x, and f prime is the derivative of x squared, which is 2x. So I could rewrite this as x squared e to the x plus 2 e to the x times x. Okay, so it's a pretty straightforward rule that we have here that allows us to take the derivatives of functions that are either just exponential functions or are some product or quotient of functions that involve power functions, which we've learned before, and exponential functions. So one thing to keep in mind, and we'll talk about this in the next video, is that in this case we're looking at only the case of e to the x. We're not looking at the case when e is raised to any other function of x. And so to do that, we'll talk about this in the next video.